Okay, so and one more comment that I want to make regarding section 4.8 is one in particular. It's called a section, little subsection they call solve a differential equation. And I've got it on my iPad here. I'm going to go over and switch over there, but I want to read to you what the first sentence that they give in the text under the heading solve a differential equation. And it makes a statement that in studies of physical, chemical, biological, and other phenomena, scientists attempt to find mathematical laws that describe and predict observed behavior. These laws often involve the derivatives of an unknown function, cap f, which must be determined. So the situation is that you've got all of these derivatives, and you got to find the function that it came from, the law that it actually came from. And it's kind of this is a true application. Again, a vast majority of you, I think, in this class are biology majors, but they're a combination of different things. This is an application of the calculus. This is kind of a cool part of the deal. But the situation is, so on my iPad, I've got this set up, that it's saying that, suppose if you want to find all functions y equal cap f of x, all right, for which when you take the derivative of that function, the notation that we use is this, you take the derivative of that, or we use lowercase f. This is a true statement. This is true. We want to find all the functions for which that's true. All right? Well, the statement that they've got going here, the way they put it is that dy dx equal to f of x, lowercase f of x, is an example of what's called a differential equation. And the solution of the differential equation is going to be this. It's actually a function. Okay? This is a solution for the problem, for this differential equation that you'll start with. So all of the antiderivatives of this will be the solution. There's a general solution, and then we'll talk more about another kind of way of looking at it, but here's an example of it. One that I think is kind of a straightforward thing. Suppose we've got little f of x is equal to 2x plus 5, okay? So this is solve a differential equation. This is it. So what it's saying is, what is the antiderivative? What's cap f of x is the question that's being asked here. So the circumstance is you got to take the antiderivative of each term. So cap f of x is going to be equal to, stop and think of it now, what did you have to take the derivative of to get 2x? It's x squared, okay? What did you have to take the derivative of to get 5? Yes, to get the constant result, we had to have plus 5x. Okay. Now, one thing I want to point out is that in general, now there is a situation where this term could have had a plus c and this term could have a plus c, but in general, in the end, we want a general solution. This cap c is going to indicate all of this is the general solution. That there's a whole, any constant added to that could also give you the derivative 2x plus 5, all right? It's a matter of just checking it. Make sure you go back and check your work. 2x, the derivative of this, 2x plus 5 plus 0. Got it. That's the solution, the situation. That's called the general solution. Now, one other thing that you're going to be asked to do is to be able to find a particular solution. In order to do that, you've got one other piece of information that you need to be given. Something else needs to be given. And an example that they give in the text, and I'm going to show this right, this is apply it to this problem I've given you, is that it makes the statement y, and the way they say it in the text is that they call it a boundary condition, in that when x equals, and for the problem I've done, I've set it up that when x equals 3, y equals 10. Okay, so you could give that as a coordinate situation. Here's the boundary condition, 3 comma 10 is what you got going here. So now we should be able to plug into the situation. Remember, this cap f of x is also recognized to be y. So another way we could write this is y equals x squared plus 5x plus c. And notice that if we plug in the x is 3 and the y is 10, the only thing we have left is c. So we will find the specific particular solution. We find the c and then put the answer down like this with c, the value we calculate. Okay? So one of the things I want you to look at is, let's go ahead and solve this problem. So the idea is plug in 3 for all the x's and plug in y for 10. 10 for y. So we have 10 equals 3 squared plus 5 times 3 plus c. 10 equals 9 plus 15 plus c. So 10 equals 24 plus c. C must equal negative 14. Therefore, we have found the particular solution. So the particular solution for the problem that we were given is going to be equal to cap f of x is therefore going to be x squared plus 5x minus 14. And it's really important that you just check and make sure it's the correct answer. When you plug in 3, do you get 10? Check it. Got it. When you take the derivative of this, do you get 2x plus 5? Yes, you do. Got it. So you do need to check and verify that the solution works. So we were given a general, so we got a general solution plus c. Then we plugged in the boundary condition and ended up solving the particular solution. This is the final answer to the problem. Okay, let me do one more example, and then it'll be a matter of you working on. Make sure you hit the problems in the text. There's several problems that are applied there in that situation. Let's do this one. All right, I've got. Let's look at. You're given this. If you're given dy dx is equal to x squared plus 2x plus 1, and you're told that x equals 3 when y equals negative 1. All right, what do you do? Right, so first thing you do is you take the antiderivative and find the general solution. We'll have a c in it. Then we plug in the 3 and the minus 1 for the x and the y, and we'll be able to solve for c, and then we give that final answer. So you're asked to solve this situation, all right? So what do we end up with? So we've got cap f of x is going to equal, okay, that first term, the power rule is you add 1 to the exponent and divide by that new power, plus 2, add 1 to the exponent and divide by that new power. Notice it's 2x, and where did 2x come from? We know that's going to x squared, right? And we've got plus 1, which is a constant, and that's going to be 1x. And then we've got plus c. So let's simplify this. So we end up with x to the third over 3 plus x squared plus x plus c. And now we're going to plug in our the boundary condition. This is f of x, or we call this y to simplify that. So we've got negative 1 equals 3 cubed over 3 plus 3 squared plus 3 plus c. That's an important part. And the goal here is to solve for c. So we end up with what? Minus 1 equals, that's 27 over 3 plus 9 plus 3 plus c. So that's negative 1 equals 9 plus 12 plus c. Negative 1 equals 21 plus c. C equals, when I subtract 21, I get negative 22. So I have found the situation, the answer. I've got the solution to the differential equation. And I end up with cap f of x then is equal to x to the third over 3 plus x squared plus x minus 22. All right, let's check it real quick and make sure it's right. So that means f prime of x is equal to, take the derivative of the first term, bring the power down front, 3x squared over 3, plus, take the derivative of x squared, I get 2x, plus the derivative of x is 1, plus the derivative of negative 22 is 0. So I end up with x squared plus 2x plus 1, which is the given problem that we started with. And if I plug in if a 3, negative 1, I should get, when I plug in 3, negative 1, f of, 3 for x, I should get negative 1 for y. So if I plug in 3, I get the circumstance that we started with, 27 over 3 plus 9 plus 3 minus 22. And that equals 9 plus 9 plus 3 minus 22. 18 plus 3 is 21 minus 22. That's minus 1. And that is the problem we were hoping for. So it checks. All right. That's doing solving a differential equation. Thank you. And hit the problems. Get going on it. And I hope I'll do some more examples on Thursday lessons. Okay. Thank you.